Good evening, everyone. I'm pleased to welcome you to the fourth installment of our Community Science and Technology Special Virtual Seminar Series, Demystifying COVID-19, presented by Pacific Northwest National Laboratory. This session, as the previous seminars have been, is being recorded, so it can be viewed at a later time. My name is Jim Sanford. They've yet to ask me to leave, so I continue to be your moderator, and I'm very excited for our fourth presentation in this 5-part series designed to share what we've learned and answer questions related to the global coronavirus pandemic that has affected us all over the past year. Before we get started, we'll go ahead and start with our usual poll to get an idea of where people are joining us from today. There will be a link being provided in the chat window that will take you to our polling feature. You can participate with your computer or mobile phone. And as you enter your answers, we'll start seeing results populating up in live time on the screen we'll switch to here in just a moment. So please click on that link and we'll give everyone a second to get their answers entered. And would just like to remind you that please click the link in the Zoom chat, which will take you to a poll where you can enter where you're calling in from. If you type your answers into the chat, only a few of us will see it, so it's a little more fun when we get more answers popping up on the screen. Here we go, looks like this will get active. There it is, great. So while these are coming in, I'll just take a moment to mention something that I did in the first couple of talks, but omitted last time. Pacific Northwest National Lab has a main campus located in Richland, Washington. But we also have locations in Sequim and Seattle, Washington, Portland, Oregon, Maryland, and Washington, D.C. So part of what we're interested in seeing with this poll is how many people from those communities are joining, but it's also just really nice to see what sort of reach we're getting. It's a little easier to tune in on a Zoom link than it is to come to the Richland Public Library for one of these talks. So we get folks from Texas, Mexico, Albuquerque, Pocatello, Idaho. Great. Well, looks like we have another wonderful turnout tonight. And just to let everyone know, Kristen in her talk tonight will have a few additional polls. So please get ready to click on another couple of links that'll show up as we're working through her talk. She does have a couple of interactive polls as she's going through. So I think we can jump back into the presentation here. And this is where I would normally take a moment to highlight some of the ways that PNNL advances the DOE's primary missions and ways that we strive to have economic impact in the communities where we live and work. But in the essence of time, I would just encourage you, if you're interested in learning more about that, please visit our website at pnnl.gov or listen to some of the previously recorded talks. I gave a little more details in talks 1 and 2. I do just want to highlight here on the screen a couple of the ways through which PNNL and Battelle strive to be good stewards in the communities where we live, and especially focus on the Community Science and Technology Seminar Series, of which these talks are a part of. Typically, these seminars are from PNNL scientists focusing on the work that's going on here at the laboratory. But as we've described over the last couple of weeks, we're doing something a little bit differently this time, and we've put together a 5-part seminar series. We're going to be 80% of the way through after today, so I do hope everyone has been able to join us for the 3 previous talks. Each talk is beneficial on its own, but the information does have a bit of a flow, and the talks build upon each other. So it's great if you can attend or listen to all 5. As an added bonus, if you have been attending and filling out the post-seminar survey, and your bracket is yet to bust there, and you can do it again tonight and next week and complete all 5, you'll get a digital certificate of completion. So far, we've heard really great talks from Steve Wiley, Amy Sims, and Katrina Waters. Again, hope everyone could attend those. If not, there's a link that's being provided in the chat feature as well as on the last screen at pnnl.gov/events, where you can find those recordings and listen to those talks. Tonight, we'll be hearing from Kristen Omberg, who will be discussing COVID-19 testing and a subject that I know is likely on a lot of people's minds over the last couple of weeks, COVID-19 vaccination. I'll introduce Kristen in more detail here in just a moment, but let me just again remind our audience of the format of these talks. Kristen will talk for 25 to 30 minutes, after which we'll have time for a question and answer series. I encourage you to type questions into the chat window as as you're listening along, you can type them in at any time. We'll be collecting these and presenting them to the speaker as time allows at the end. As we did last week, we'll be having an extra 15 minutes. So Kristen has volunteered to stick around until 6:15 tonight. Again, the number of questions has been really outstanding. I appreciate all the engagement from the audience. So please continue to type those in, and we will have quite a bit of time tonight to answer those. We're again joined by our panel of community representatives who will help us spur the question and answer series. So I'll take a quick second to introduce our community reps. We've started from the left, we've started from the right. So I'm just going to go out on a limb here, start with Justin Rafa. He is the artistic director of the Mid-Columbia Master Singers. Justin, welcome tonight. Welcome a few comments.
Thank you. You know, I've never taken a COVID test and have been thoroughly confused by the variety of tests that have been rolled out. So I'm pleased to learn more on that front today. My sector, choral music folks have talked a lot about the PCR test, but we realized it would be some time before that test became commercially available and affordable for most organizations.
Great. Well, thanks for joining us. Next, we have Martine Valadez, the Regional Director for Heritage University's Tri-Cities campus and the Interim Executive Director for the Tri-Cities Hispanic Chamber of Commerce. Martine, how are you tonight, and what do you hope to gain from today's talk?
Yes, so I would like to learn more about the testing itself. I actually finally took my first test last week and it went fine, but also about the vaccine and kind of some concerns about the hesitancy of some people to take the vaccine, and I'll have a question about that later. So thank you so much.
Great, thank you for joining us. Next, we have Loanne Ayers, the President and CEO for United Way of Benton and Franklin Counties. Loanne, how are you?
Hey, I'm great. You know, in talking with local nonprofits and small businesses, there is a lot of confusion about the different types of tests out there. And so my interest tonight is really learning more about what do employers need to know about the different types of tests, and more specifically, what does that mean for safely bringing employees back to work?
Thank you. Those are very relevant points. Finally, we have Kate McAteer, the Vice Chancellor for Academic and Student Affairs at Washington State University Tri-Cities. Kate.
Good evening, Jim. I'm really interested in learning more about the vaccines in school-age children, perhaps trials that might have been done with that age group and the efficacy of the vaccines in children.
Excellent. Well, thank you again to our panel for joining us. Look forward to hearing from you guys in the question and answer series. And without further ado, it gives me great pleasure to introduce Kristen Omberg. Dr. Kristen Omberg is the group leader of the Chemical and Biological Signatures Group at Pacific Northwest National Laboratory. Her technical work entails developing solutions with practical utility in addition to policy implications. She recently worked with the U.S. Departments of Energy and Health and Human Services to evaluate methods for COVID-19 specimen analysis. She received her PhD in chemistry from the University of North Carolina at Chapel Hill. Welcome, Kristen. Take it away.
Thanks, Jim. I appreciate that nice introduction. And I'm looking forward to hearing the questions that you all have tonight. Tonight, we're going to discuss two important parts of the viral infection cycle: detection of infection and vaccination. If you've been tuning into the series, you've seen this slide before, and you know that a virus is a non-living particle. Tonight, we're going to discuss viruses, and in particular, two pieces of a virus: its genetic material, which in this case is RNA or ribonucleic acid, and the proteins that decorate its surface. That's because the genetic material and the surface proteins are the basis for both testing and vaccination. The surface proteins are also really important because they're how your body recognizes that it's been infected by a virus. And in response to that recognition, your immune system makes complementary proteins called antibodies, which bind to the surface proteins and disable the virus. This is some of the terminology that we're using in the series. In particular, tonight we'll be talking about vaccines, which is a preventive measure to build immunity against a specific disease, and mutations, changes to the genome of a pathogen or organism that might affect transmission, symptoms, prior immunity, or even the effectiveness of a vaccination. But as Jim noted, we're going to have some polls tonight. So the first poll is coming up right now. Nope, excuse me. And that poll is, the Food and Drug Administration has approved 41 tests for influenza or flu. About how many do you think are currently authorized for COVID-19? 10, 40, 190, or 340? So you can text PNNL. Oh my goodness, look at you there. There's the results, that's fantastic. Okay, while we're waiting for these numbers to come in, I don't know about you, but I find all the news releases about new COVID tests confusing and a little draining. We have 41 tests approved for flu in the United States. And you'll note that I'm using a little bit different language in this question here. The tests for flu are approved. The tests for COVID are emergency use authorized. So emergency use authorization means that the FDA has decided that the benefits of the test outweigh the risks. It doesn't mean that a test is perfect, and it doesn't mean that a test is fail-safe. And that's part of the reason I think the media coverage is so confusing, because in the US, we're used to really good diagnostic tests. Those 41 flu tests are outstanding. And what we're seeing right now is tests that have been authorized at a lower standard than what we're used to. And some of these tests have proven to be less accurate than we might like. Wow, okay, so the 4% of you who answered 340, you're actually correct. There are 340 approved tests for COVID-19, and that number goes up regularly. Oh dear. I seem to have lost. Oh dear, I'm very sorry. I seem to have lost my tab here. Okay, so we're going to start tonight with a brief review of the components of the coronavirus. Then we'll talk about common testing methods. Then we'll talk about vaccines, and then finally where we go from here. So first, the components of the coronavirus. You've probably seen a picture or something, either this picture or something like it, in the last year. This is the coronavirus. Coronaviruses are RNA viruses, which means that their genetic material or their genome is made of ribonucleic acid. If we cut this virus open, we can see its components. There's two important components we're going to talk about tonight. The first is the spike protein, or S. S is shown here as a little yellow spike decorating the surface of the virus. The spike protein, which is also called spike glycoprotein, spike antigen, S antigen, or just S, is a surface protein that helps the virus get into cells so it can replicate. The genetic material, or the RNA, which is the pink spiral in the middle, contains the code that the virus needs to reproduce itself, to replicate in your body. All of the diagnostic tests, all 340 of the diagnostic tests that are currently authorized, detect either spike or RNA. Testing falls broadly into two categories: diagnostic tests, which detect S or RNA and tell you whether or not you're currently infected, and immunoassay or antibody tests. We're going to talk about those tonight and how they're different. We're also going to touch on home tests and talk a little bit about why we collect nasal swabs, which if you've had one, you probably didn't enjoy. So most of the rapid or point of care tests detect the spike glycoprotein, or the S antigen, which is that yellow protein on the surface. Antigen is just a technical term for a protein that's on the surface of a virus. If you've gotten a test in a doctor's office, that's a point of care. So these tests are commonly run in doctor's offices. The test that you get in the doctor's office is probably an S antigen test, which means it was looking for the presence of that yellow protein. And here's how it does it. As I mentioned previously, when your body detects a virus, it makes complementary proteins called antibodies, which bind to the surface proteins, or the antigens, in this case, spike antigen. The antibodies block the virus from getting into your cells until it can be destroyed by the immune system. We can make those antibodies in a laboratory and use them for detection. And to do that, we attach a little molecule to the manufactured antibody that either fluoresces or changes color when the antibody binds to the antigen. The test measures the fluorescence or the color change. If you're familiar with the home pregnancy test, it is also based on this type of technology. S antigen is best detected when there's a lot of intact virus in your system, which usually corresponds with the development of symptoms. So studies show that S antigen tests are most accurate when you take them right before symptoms start and in the first 7 days after symptoms begin. After 7 days, they're less accurate. So there's many benefits to the S antigen test, and there's also some drawbacks. They can be run in a doctor's office, and a lot of them run on the same equipment that we use to detect influenza. So there's a lot of resources out there for running these tests. It only takes about 15 minutes from a swab to a result, and a positive result means that you are currently infected with the coronavirus. Unfortunately, compared to other tests, S antigen tests are relatively insensitive. So infected people may still receive negative results, particularly if they're outside that window of time between when symptoms develop and 7 days after. If you're 10 days after, the virus is declining in your system, and an antigen test is less likely to be reliable. And because there's a relatively narrow window of detection, which is less than 7 days, the antigen tests typically won't pick up people who are pre-symptomatic or late symptomatic. And that's important because we do believe that pre-symptomatic people are capable of spreading infection. The other common test detects RNA. So RNA tests are usually run in the lab, and they're based on a nucleic acid amplification technique that's called polymerase chain reaction. They're often referred to as NAATs for nucleic acid amplification test, or PCR for polymerase chain reaction tests. And these are the tests that you need. For example, if you want to travel to Hawaii, you have to have a nucleic acid amplification test, or to another state with restrictions. Nucleic acid amplification, or PCR tests, are based on a really cool enzyme that's called Taq polymerase. And it comes from a bacterium that lives in hot springs and is really active at high temperatures. And it kind of looks like a little Pac-Man, for those of you who are familiar with that game. Taq polymerase is sort of a high temperature copy machine for RNA. If you have a sample with SARS-CoV-2 in it and you heat it up with Taq polymerase, the enzyme becomes very active and it makes a copy of a specific part of the RNA. If you cool it down, then you have two copies now. You have the original and you have the copy the Taq polymerase made. And if you set this up correctly, when it does that, it releases a little molecule that fluoresces. If you heat and cool the sample repeatedly, Taq continues to make additional copies and releases more fluorescent molecules each time. So the fluorescence amplifies by a factor of 2 with each heating and cooling cycle, and that's why we call this nucleic acid amplification. The amplification of the fluorescence is what we detect, and because we get this factor of 2 copy every time we run the heating cooling cycle, this is an extremely sensitive test. If there are about 500 virions in your swab sample, we will be able to detect it. Because of that, studies show that nucleic acid amplification, or PCR tests, can detect the virus several days before symptoms begin and for many weeks after. So it's much more sensitive than the antigen tests, and there's a much longer window of detection that also includes pre-symptomatic individuals. So there's a lot of benefits to the nucleic acid amplification, or PCR tests. They're typically considered the gold standard of diagnostic tests in this country. If you have an unusual disease, they will diagnose it using PCR because it's very sensitive and it's very specific. The current RNA test is extremely specific to the 2019 strain. It detects the 2019 strain, and it really only detects the 2019 strain. Because the tests are so sensitive, we can detect infections before people develop symptoms. So if you've been exposed, about 5 days after exposure, we can typically detect whether or not you have been infected and are going to develop the disease. And that's important because people can transmit this disease before they're overtly symptomatic. But there are some drawbacks to PCR. As was noted earlier, they tend to be expensive. They usually have to be run in a lab, not a doctor's office, and they take 4 to 6 hours to process results. And second, people who test positive may test positive for months after symptoms subside. And while that's something that we haven't talked a lot about before, that's actually something that's not unique to coronavirus. If you get flu, you will test positive by PCR for at least a month after you start having symptoms. It's because a PCR test is really sensitive and because RNA seems to stick around for a while in the respiratory tract. And that's why we don't use testing to clear people after infection. We know that people will test positive by PCR long after they recover from the disease. In addition to the diagnostic tests, there are a lot of immunoassay or antibody tests available for SARS-CoV-2. So as we discussed earlier, your body makes antibodies in response to a viral infection. And those antibodies bind to the virus to block it from getting into your cells and to tag it so that the immune system can come along later and destroy it. Just like we can manufacture antibodies in a lab, we can manufacture antigens in a lab. So if we manufacture antigens in a lab and add a little molecule to them that changes color when it binds to the antibodies, we can detect whether or not there are antibodies circulating in your system by measuring that color change or their fluorescence. Now, since your immune system makes antibodies in response to an infection, antibody tests don't tell you that you're infected right now. They tell you that you were infected at some point in the past. And this chart shows you when natural antibodies are typically detectable in the body. So antibodies start to be detectable about a week after symptoms start. And then they decrease over a period of time that, as best as we can figure, seems to correlate with case severity. In practice, we don't use antibody tests a lot. They're often used to detect autoimmune disorders like lupus, or to assess the effectiveness of previous vaccinations. So for example, if we were trying to decide if you needed a new measles vaccine, we could do an antibody test for that. This is the first time we've seen them in widespread use for an infectious disease. And unfortunately, it's not clear to me that they were really ready for prime time. That's because they've got both high rates of false positives and high rates of false negatives. So it's hard to say what an individual would do with the results from these tests. So far, I've seen two really good uses of antibody tests. The first is that the Red Cross is using it to identify potential plasma donors to help treat patients fighting infection. The use of convalescent plasma has shown some effectiveness in treating severe cases of COVID-19, so looking for possible donors is a great use for this test. Antibody tests can also be used to estimate how many people in a community have had COVID-19. There are some studies that have been published, for example, on New York, where they have looked at the prevalence of antibodies in the population to try to estimate what kind of herd immunity they have. But it's important to remember that the antibody tests won't tell you if you're currently infected, and they're prone to false negatives as well as false positives. So now is time for our next poll. So the Food and Drug Administration has authorized about 70 COVID-19 antibody tests for use in the US. So as we noted, there are 340 other tests. There are about 70 antibody tests currently on the market. How many do you think they have withdrawn from the US market? How many have been submitted by manufacturers and then removed? So a moment ago, I mentioned that this is the first time we have seen these tests in widespread use for an infectious disease. And while you're voting, I thought I'd tell you a little bit about why they produce false negatives and false positives. First, we are not 100% sure how antibodies build in a person's system, and we're not sure what kind of levels will manifest in a particular individual. So there have been a lot of people who have had diagnosed COVID-19 who have then subsequently had negative antibody tests. The second thing, people have been doing some elegant studies to try to determine cross-reactivity. So to determine whether or not we get false negatives with these tests, people have been testing them with blood that was collected and banked prior to 2018. So prior to 2018, we didn't have COVID-19. So if we get positives in what I guess would be called vintage blood samples, that indicates there's cross-reactivity, that the test is probably detecting antibodies that are hanging around from an infection with a different human coronavirus, most likely one of the ones that produces mild cold-like illness. So you guys are right on. The answer is 250. There are about 70 COVID-19 antibody tests currently authorized for use in the US, and there are 250 that are on the FDA's do not use list. Home tests. There's a growing number of home tests available. Costco has a home test. I'm not plugging Costco. Everlywell has a home test. I'm not plugging Everlywell. I think LabCorp has a home test. So there are about 10 home diagnostics tests for use right now. And they are all based on molecular nucleic acid PCR technologies. So these are all solid tests. The only question is whether or not you think you can collect as good of a sample as a medical professional. And that brings me to my last topic under detection, which is why do we swab? So if you've had a COVID test, I'm sure you have asked yourself that question. I have had 3, and every time I ask myself why the nasopharyngeal swab. The reason we usually collect respiratory tract swabs is that we know that the virus lives in the respiratory tract, and studies have shown that the concentration of detectable virus is usually higher the closer we get to the lung. There's been a lot of press lately on saliva samples, and saliva does seem to be a reasonable matrix to detect the virus in people who are symptomatic. But just about everything that I want to do in the morning interferes with the test. So toothpaste, mouthwash, caffeine, fruit, orange juice, milk, chocolate milk, all of these can cause a false negative test. So that doesn't mean that saliva tests don't work, but if you're planning to take one, I would treat it like a cholesterol test and fast overnight prior to sample collection. So to summarize the common testing methods, we have 3 different methods that are available for testing for COVID-19. Antigen and molecular tests, which are diagnostic tests, they detect current infection, and immunoassay tests, which identify previous infection. Each one has its own pros and cons. Antigen tests detect current infections. They can be run in a doctor's office in about 15 minutes. So they're very convenient, but they're a little bit less sensitive. They're often being used in settings where tests can be repeated frequently. For example, right now, the women's teams in the NCAA tournament are being tested daily using antigen tests. So if you can test frequently enough with an antigen test, it's likely you'll be able to overcome that lack of sensitivity by hitting the detection window at the right time. Molecular tests like PCR can be used to detect infection in pre- and late symptomatic individuals. They're very sensitive and they're regarded as the gold standard for clinical diagnosis, but they have to be run in the lab. And they take 4 to 6 hours, and people can test positive for months because the RNA sticks around. In an interesting dichotomy, and this is causing some controversy in the press, the men's teams in the NCAA tournament are being tested daily using PCR tests. Immunoassay tests identify previous infection. They're fast, but they're prone to false positives and false negatives. We haven't commonly used them during epidemics or pandemics, but I'm actually really curious to see where they'll go after this, because if we can improve them, they could be really useful in the future. Which takes me to where we go from here scientifically. One of the things none of the tests will tell you is if you're prone to infect someone else. That's unfortunate, but we're just not capable of saying that one person is more infectious than another using any of these tests. Defining that correlation is an active area of research, and I hope that we will be able to get to that point. The second is diagnostic tests are expensive. They can be very slow to get results, and they're a bit inconvenient. So there's a lot of research going on into tests that can be run at home, tests that are inexpensive to use, tests that we can get out there in the hands of individuals, which could really be a tremendous paradigm change in public health. And third, as I mentioned, the immunoassay tests have a lot of potential, but they need to become more sensitive and more specific so that their results are meaningful. So that concludes the discussion of testing tonight, and next up we'll discuss vaccines. First thing we're going to discuss is the 4 types of vaccines currently in development. Then we'll discuss the variants that are emerging worldwide and whether they might impact vaccine effectiveness. So this is our last poll of the night. There are 26 different flu vaccines in the US. About how many different COVID-19 vaccines do you think are in development? Is it 12, 57, 70, or 100? And you guys are fast. So I'll tell you, those of you who answered 12, answered the number that have been authorized by at least one country somewhere in the world. In the US, we've authorized 3, but across all countries, 12 are authorized. Worldwide, there are about 70 that are currently in development. All right, so going back to this slide, which we looked at earlier in the presentation, if you remember what we talked about on this slide, which is RNA and spike glycoprotein, you know almost everything you need to know about vaccines, because all of the current vaccines rely on either spike glycoprotein or RNA or both. So as I said earlier, the RNA is a code that contains everything that the virus needs to replicate itself. It's 30,000 nucleotides long. A nucleotide is just a special molecule that makes up RNA. So if I stretch it out in a long line, I have 30,000 nucleotides. And that 30,000 nucleotide sequence is a code that contains all the directions for making a new virus. Toward the end of that 30,000 nucleotide sequence is a 4,000 nucleotide sequence that codes for spike glycoprotein. And this is a 3-dimensional rendering of spike glycoprotein. It's pretty complicated. Spike glycoprotein is made up of 1,273 amino acids. An amino acid is a special little molecule that makes up a protein. When a protein folds, when a protein is as long as spike glycoprotein, and it has to fold, it folds into a 3D conformation that then binds to your cells and then allows the virus to get in. And that 4,000 nucleotide sequence that codes for spike glycoprotein is the basis of the mRNA vaccines. So mRNA vaccines start with just a little sequence of RNA. They don't start with virus. They start with a sequence of mRNA that codes for spike glycoprotein. That sequence gets encapsulated in a lipid nanoparticle, and a lipid nanoparticle is just a fancy name for a really specially designed glob of fat. This glob of fat is very important because RNA by itself is extremely fragile. So that lipid nanoparticle protects the RNA in the vaccine and keeps it from falling apart. So in an oversimplified sense, if we take a whole bunch of mRNA sequences and we encapsulate them in a whole bunch of lipid nanoparticles, you get an mRNA vaccine. One of the interesting features of lipid nanoparticles is that they cross cell membranes very easily. So when we inject this vaccine into you, those lipid nanoparticles go into your cells where they release that little RNA sequence that makes spike glycoprotein, and they direct your cells to make spike. So they turn your cells, instead of into a virus factory, into just a spike glycoprotein factory. Your immune system then recognizes the spike as a foreign invader, and it makes antibodies against it so that when you're exposed to coronavirus in the future, your immune system says, wait a minute, that's spike glycoprotein. We've seen that before. And it's ready to attack. There's currently 2 mRNA vaccines in the United States that are authorized for emergency use, and you probably know them best as the Pfizer-BioNTech and the Moderna vaccines. In addition to the mRNA vaccines, there are viral vector vaccines, and they work also by delivering that S gene into your cells and directing your cells to make spike glycoprotein. But instead of using a lipid nanoparticle to encapsulate that S gene, they use a virus. In this case, it's an adenovirus that can infect your cells but can't actually replicate itself. All it can do is drop its payload of that S gene. And so the only thing that can be produced from it is more spike glycoprotein. But that viral vector acts to stabilize the genetic sequence just like the lipid nanoparticle does. If it wasn't inside the viral vector, it wouldn't be very stable, either in a vial or in your system. So again, this is a little oversimplified, but if you take a bunch of S gene sequences and load them into viral vectors, you have a viral vector vaccine. Now, because the carrier is a virus, once it's inside your body, it's capable of getting into your cells the same way a virus would. And once it gets there, it leaves the S gene, which then produces spike glycoprotein. Your immune system recognizes that as foreign and makes antibodies against it so that when you're exposed in the future, your immune system is ready to attack. There is one viral vector vaccine authorized for use in the US, And you probably know it as the Johnson & Johnson vaccine or the Johnson & Johnson Janssen vaccine. There are two more types of vaccines that are in development worldwide, but we haven't seen a whole lot of them in the US. The first is the subunit or peptide vaccine. A subunit or peptide vaccine just relies on spike glycoprotein, stabilized spike glycoprotein. And that spike is made in an engineered bacterium like this. This is my friend E. coli, so it's non-pathogenic E. coli. Or in yeast, we add the little gene to yeast, or we add it to a friendly bacterium, and then we ferment it just like beer, except instead of making alcohol, we're making spike glycoprotein. Once the engineered bacterium or yeast produce a bunch of spike, it's stabilized, and then it gets injected into a person. Your immune system recognizes it and makes antibodies against it. So when you're exposed in the future, the immune system's ready to attack. There are a couple of vaccines available for this worldwide, and a couple of them have been approved. I think the most prominent one was developed by the Vector State Research Center of Virology and Biotechnology in Russia. It is authorized for use in Russia, and it's called Epivac Corona. I haven't seen a whole lot about it in the United States. The fourth type of vaccine you might be familiar with. This is the inactivated or attenuated virus vaccine. This is the old school vaccine. If you got a measles, mumps, and rubella vaccine or a polio vaccine, they are both examples of inactivated or attenuated virus vaccines. So these vaccines are based on virus that's treated either with heat, radiation, or chemicals to make the virus less harmful. And then that treated virus is what goes into the vaccine. This is a really solid vaccine method, but one of the things that I think gets overlooked is it involves growing a whole bunch of virus first. So if we're growing a whole bunch of measles, mumps, or rubella, we have vaccinated people, and that's such a big deal. If we have to grow a whole bunch of coronavirus, it's not only time consuming, there's a risk associated with growing that up. So we're not pursuing this in the United States, but other countries like India are pursuing it. So once you grow it and inactivate it, you can inject it into a person. Your immune system recognizes spike, and your body makes antibodies against it so that when you are exposed in the future, it's ready to attack. And one thing that's important about this vaccine, this is the only type of vaccine that actually relies on the virus itself. None of the other vaccines rely on an actual whole virus. So none of these are like the old vaccines where there is a chance that you might actually get sick. So to summarize, we have four types of vaccines. We have the mRNA, also known as the Moderna or the Pfizer-BioNTech, the viral vector, also known as the Johnson & Johnson and that Oxford AstraZeneca. We have the subunit or peptide vaccine, inactivated or attenuated virus vaccine. All four of these trigger an immune response that leads to the production of antibodies to spike glycoprotein. And when your immune system responds, much like when you get an infection or you get a cut or a bruise, you get some inflammation, and that's just a symptom of your immune system working. It's not a symptom you've been infected with anything, but you get an immune response that means that your body's producing antibodies, and that immune response looks like pain and swelling at the vaccine site, low-grade fever, chills, fatigue, and headache. So that's why people sometimes think that they're actually sick after they get the vaccine, but they're not. The vaccines that are approved in the United States don't contain any replication-competent virus. So there's actually no way that they can make you sick. That also means that there's no way that you can infect someone else. That's something my husband asked me about this, is if I get vaccinated, can I then infect someone else while I have side effects? Not with the vaccines that are approved in the United States. So an immune response to the vaccine, the side effects that people are experiencing, it doesn't mean they're infected and it doesn't mean they're infectious. It means that their immune system is working as designed. So the big question with the vaccines right now is, what about the variants? So if you remember spike glycoprotein, this is spike glycoprotein in all its glory. It contains 1,273 amino acids that fold in a specific conformation that allow it to dock with the ACE2 receptor on your cell so that the virus can get inside your cell. The variants all contain different amino acids at specific locations in this really complicated structure. So this is a gene map, and I know it's probably difficult to read, but you don't have to actually read it unless you want to know what the variants are. In the 1,273 amino acids that are contained in spike glycoprotein, the UK strain that people are talking about a lot has 9 that are different. So 9 out of 1,273. The South African strain has 11 that are different out of 1,273. The Brazilian strain has 10 changes. The New California strain has 8. So the question really is, how many changes can occur in spike glycoprotein before your immune system stops recognizing it based on the vaccine? And the unfortunate answer is that we don't really know. So far, the studies from laboratory experiments show that the approved vaccines provide protection. But one thing, the authorized vaccines provide protection. But one thing to remember, these are emergency use authorized vaccines. They're not full up approved vaccines, and they may not keep you from getting completely sick. So all of the vaccines that are currently authorized in the United States reduce disease severity, hospitalization, and death. They don't actually promise that no one will ever get the virus again. And that's why it's important to keep wearing masks. And it's important to get vaccinated because what this virus is doing right now is just what viruses do. It's adapting to its environment. So the longer it continues to circulate, the more it will continue to mutate, and the more likely we are to end up with something that is substantially more dangerous. So where do we go from here scientifically? First, like I just mentioned, we can't say with any certainty how many amino acids in spike can change before the virus starts to evade vaccines. That is an area of active research. Second, the mRNA vaccine and the viral vector vaccine are relatively new, and we're at a really interesting crossroads in vaccine and therapeutic development now that we have these 2 new platforms. The viral vector vaccines are relatively new. If you followed the news about Ebola outbreaks and the Ebola vaccine, Johnson & Johnson's Ebola vaccine is made on that technology. Companies are also working on a tuberculosis vaccine that is based on the viral vector technology. The mRNA vaccines are brand new, but the companies are working on Zika and Epstein-Barr virus vaccines, as well as influenza virus vaccines. And there's a lot of interest in using these platforms to deliver drugs or therapeutics now that we know that they can successfully deliver mRNA. So it'll be exciting to see where they go. So finally, where are we going from here in general? This is an epidemic curve. So for an isolated population, when a new disease emerges, everyone is susceptible. That's the curve in blue. Over time, the disease spreads, people become infected. That's the curve in red. And then they recover and they have immunity from the disease for a period of time. So we call them non-susceptible, and that's the curve in green. Right now, we're somewhere in the middle of the red. I am not sure where we are in the middle of the red. We're definitely not at the beginning, but I'm not willing to say that we're completely on the downward slope yet. Vaccination changes those curves by moving people directly from susceptible to non-susceptible without them going through that infected phase. And by reducing the number of susceptible people, the chance of transmission ends up being lower. So you've probably heard a lot about herd immunity. Herd immunity isn't a number, it's a concept. And the concept is that by reducing the number of people who can transmit a disease, we reduce the rate of spread and we protect those who are still susceptible. In this graphic, the infected people are in red, the non-susceptible people are in green. The more people we have are in green, the less likely it is that the people in blue, who are often our most vulnerable people, for example, very young children or the immune compromised, are to be infected. So herd immunity isn't a magic number, but every vaccine we give gets us closer to herd immunity. So every single vaccine is important. With that, Jim, I am happy to take some questions, and I wanted to end tonight by sharing a picture with you. This is my parents. This is right after they received their first dose of the vaccine, which they got at Prosser Memorial Hospital. I saw we had some people in Prosser tuning in tonight. I have to give a shout out to Prosser Memorial for their vaccination clinics, which are extremely well run. And also to the Benton Franklin Health District, which is working really hard to get the vaccine out there right now. All right, that's all I got. Jim, do we have any questions?
Yep, we sure do. Thank you so much, Kristen. Really appreciate that talk, all that useful information. We have about 240 people that have been joining us tonight, and questions are certainly coming in at a nice pace here. As we mentioned at the top, let's start with some quick questions from our community representatives. So Justin, Rafa, we'll start with you. What would you like to ask?
What type of test is offered at the free drive-through CBC West testing site? And I'm curious, is there any reason to pursue having to pay for a test at an alternative site, pharmacies, urgent cares, et cetera, beyond the potential scheduling limitations of when the CBC West site is open?
The CBC West site, which is being administered by the health district, is running a molecular or PCR test, and it's a really good test. If I didn't have access to testing through my work site, I would absolutely be going to the county site. For convenience, the Benton Franklin Health District also has a list of testing sites across the Tri-Cities, and it tells you which test each site is running. So if you go to their COVID-19 page, you can find it under the test site locator. But yeah, I really respect what they're doing out at CBC West. They're doing a fantastic job.
Thank you.
Thank you, Justin. Martine Valadez, we'll move to you next. Do you have a question you'd like to ask?
Yes, and thank you, Kristen, for your great presentation. I know a lot more about the test and how they are, and actually I had to go see my parents for the first time after a year, got the test and it's negative. I got it down here right as I left the airport. I stopped first before coming home.
Nice.
Get the test, so great. So my question though is about the vaccine. So unfortunately, in the Latino community, there's been some polls taken, and it's estimated that when asked, people of Latino heritage, between 33 and 37% of the people say that they will not take the vaccine if it's available to them, which of course I wonder about. So I know you talked about this just a little bit, you touched on it, but I wanted to, what kind of information can I share with individuals in the community to, I guess, just provide them more education for them to make a more educated choice about the vaccine itself?
Yeah. So the hesitancy to get vaccinated seems to be due to a variety of reasons. One of them is lack of trust in the clinical trials and the concern about whether or not people of color were adequately represented in the vaccine research. You can pull up the raw data on all three of the tests for the vaccines, but I like to go to the Kaiser Family Foundation site. They have a COVID-19 vaccine monitor where they pull together all the data. And one of the things that I find really heartening is that the trials of all three of the currently approved vaccines had great representation from people of Hispanic ethnicity, with 20% or more of participants from that community. And that's really good for clinical studies. I'm really pleased to see how much they were reaching out on that. Some of the hesitancy seems to be due to getting COVID from the vaccine or having side effects that might cause you to have to take sick days or miss work. If it's concern about getting COVID-19 from the vaccine, I hope you feel like you know enough now to talk about how the approved vaccines can't give you COVID. The side effects and concerns about missing work, that's a real concern. So I looked through today at the three approved vaccines, and the Johnson & Johnson vaccine does have a slightly lower reported set of side effects. It's also only one dose. So if people are concerned about the side effects and missing work, I would encourage them to go for that one dose and get the Johnson & Johnson. I hope that helps.
Yes, thank you. And we were fortunate to get that vaccine, so thank you.
Great, thank you, Martine, for that. Let's move to Loanne Ayers. Loanne, do you have any reflections or a question for Kristen?
I do. How do I know when my employee is safe or unsafe to be around others if she tests positive, but the RNA positive test results may last many months after her symptoms disappear?
Yeah, that is a hard one. And I really wish that I had a better answer for this question. Unfortunately, the current test won't tell you if someone is safe. So the best thing that we can do really is compare it to influenza. If we have flu, we don't usually test people to determine whether they've recovered from the flu. We watch their symptoms, and we assume that after their symptoms subside, that they are less likely to transmit the disease. And that's because at that point, their immune system has mounted a response. It has the virus on the run, right? It's actively destroying the virus. And so we assume that they are less likely to transmit the disease. And that's why the recommendation is a certain period of time after their symptoms subside. I wish we had a better test for that.
Great, thank you. Now we'll round out our community representatives' first questions with Kate. Kate, how are you?
Great, thanks, Kristen. That was a great presentation. So my question is around vaccinations for kids. So I believe the 3 current vaccines are safe for 16-year-olds and above. What are any of them in trial for younger children?
They are actually. Johnson & Johnson, Pfizer, Moderna, and AstraZeneca are all performing clinical trials with school-age children. AstraZeneca actually started their study first and is including children down to the age of 6. Pfizer, Moderna, and Johnson & Johnson are currently testing in children ages 12 to 15, but they are talking about expanding their studies to include children as young as 6 months once they're done with that. So the best estimates that I'm seeing are that given the time it takes to run these tests, we might be able to vaccinate school-age children in the fall, but probably not before the start of the school year.
Thank you.
Great, thank you for those questions. I'm gonna hop right into questions coming in through the Zoom chat. It's popping. So first off, what is current data on if you are vaccinated, how likely you might be to get sick or infect others?
The current data is still evolving on that. And it depends a little bit on the vaccine you get and the amount of time you are out from your vaccine. But in general, these vaccines are cutting the likelihood of severe disease by 70% or more. So the Johnson & Johnson is somewhere around 70%. The Pfizer and Moderna are up in the 90s. And the further out you get, the better that data seems to look as your body again has a chance to build up that immune response. So the odds of getting severe disease are very low. The odds of getting any disease are not zero, unfortunately. So people have gotten the vaccine and then have still contracted clinically confirmed cases of coronavirus, which is part of the reason that you're hearing a little bit of an outcry from the public health community about raising mask restrictions. Until we have a vaccine that we know is stopping the transmission, I think we'll still see people who are inclined to say that we need to continue wearing masks.
Got it, thank you. In terms of testing, why have so many people that are sick with symptoms consistent with COVID-19 tested negative?
Yeah, there can be a couple of reasons for that. I think the most common one is that there's other respiratory viruses that are circulating. You know, we didn't see a whole lot of flu this year, but I'm sure that there was some flu that was out there. Right now with allergy season, I don't know about you, but I've got some congestion and my nose is a little bit runny. So there are other things that look very similar to COVID-19. And that's partly because the symptoms that you get from a virus, a lot of them are due to your immune system. So if your immune system is attacking anything, whether it's pollen or influenza or COVID-19, you get similar symptoms. The other thing is that there has been confusion around when the tests can and should be used. So the antigen test, we saw people test positive and negative with the antigen test, and then have that result reversed by PCR earlier in the year. And that has to do with the sensitivity and the detection window. So the antigen tests are good tests if your viral load is high, which means they're good tests between the day you develop symptoms and 7 days after symptoms. If you're pre-symptomatic, if you don't have any symptoms, the odds of you getting a false result on an antigen test are much higher. And so that is, I think, why we have seen some of the test results come back as different when we look by PCR.
Great, okay, that makes sense, thank you. Kind of related to that, a lot of people who have contracted COVID remain symptom-free, so maybe they don't get tested. What is any thoughts on what's going on differently in their bodies versus those who become sick?
No, and I find that really fascinating. We got to work a bit with the FDA earlier this year on testing, and it's really amazing to me. Some people can be asymptomatic and still have a fairly high viral load, and we don't know if that means they can transmit disease or not. Pfizer just released the first data on prevention of asymptomatic infections. And the Pfizer vaccine does seem to prevent asymptomatic infections. That doesn't mean the other two don't. It just means they haven't actually measured that and released the data yet. So I'm hopeful that the vaccines will be enough to stop that. But in the meantime, if people can continue to get the disease and be asymptomatic, that's just another reason why we should all invest in a fun set of masks.
Nice. Okay, cool. Is there any idea how long we can expect the vaccines to provide immunity?
Unfortunately, I don't have a good answer for that. They are continuing to look at the window of immunity in the studies. They're also continuing to look at how long people who've previously had coronavirus still retain their immunity. But unfortunately, what we're able to say is, sort of up to a year, because that's the data that we have. One of the things that is an unknown in that is the mutation of the virus. So the longer the virus continues to circulate and the more it mutates, the more likely it is that it will mutate into a variant that can reinfect someone or that can infect someone who's vaccinated. So that's an excellent question, and I wish we had a better answer.
Sure. Related to that, we think of the flu vaccine, one that we get every year. Do you think that this, A, why is that? Is that new strains of the flu? Is that our immunity naturally fading? And then B, is this going to be a situation where maybe we're encouraged to get a vaccine yearly for this COVID?
It may well be. With the flu vaccine, flu mutates at a rate that's 4 times faster than what we've seen for coronavirus, if I recall my statistics correctly. And so it does mutate, and every year we can get different flu strains. So that's why we have a new vaccine every year. It's to deal with those slightly different mutations. And also, we are really fortunate that we have good vaccines like the measles, mumps, and rubella vaccine, which is a sterilizing vaccine. So if you get the vaccine, you don't get it. But flu and coronavirus are likely to be severity reducing vaccines, which means you get the vaccine, it's going to prevent you from being hospitalized. It's going to reduce the mortality associated with it, but it may not completely prevent you from getting that disease. But one of the interesting things, Moderna has already announced that they are working on a combined influenza coronavirus vaccine. And I do think that's probably the next thing that we're going to see gearing up for next year.
Interesting. I had not heard that. Let's talk a little bit about side effects real quick. Martin touched on it briefly in his question. So first of all, are there any concerns for long-term side effects from COVID vaccines?
There have been some adverse reactions reported that typically have to do with how the shot's administered. And I don't understand them 100% correctly, but there have been some cases when people getting vaccinated, the needle has hit a nerve that has caused some ongoing pain. It's interesting. I was looking through the side effect studies today to see how the different vaccines compare. And if you look at the side effects, they are most frequently very short duration. They are most frequently pain at the injection site, headache, and fatigue. And interestingly, in all of the studies, at least 30% of the placebo group, the control group that didn't get the vaccine, also reported headache and fatigue, which implies that there's probably a lot of headache and fatigue that people are attributing to vaccination that may just be because we're all fatigued and more prone to headache these days. I know I am.
True. Good point. Good point. So, okay, to counter that, then people that are not having side effects after their vaccinations, does that indicate that they're not mounting a proper response? They're less likely to be protected?
Yeah, fortunately, no. And I say fortunately because my mother breezed through her vaccine, both doses, and her arm never even hurt. So here's what we know about the side effects and the effectiveness. In the clinical studies, about up to 90% of participants reported some sort of side effect. So either that pain at the injection site, headache, or fatigue. And interestingly, up to 60% of the control group reported headache and fatigue as well. So we can assume that there's sort of a baseline level of headache and fatigue in the general population, but about a third of people who participated in the studies actually had a genuine vaccine-induced side effect. But in the same studies, the vaccine prevented severe disease in more than 2/3 of the participants. So there's a good chunk of people in these studies who did not have a vaccine-related side effect, but still got the full benefit of the vaccine. So if you have a reaction to the vaccine, it's a great verification that your immune system is working. But if you don't have a reaction, I don't think it's a reason to stress.
Sounds good. Thank you. I'd like to quickly hop back and let community representatives ask another round of questions. I know that there's a lot in the chat that are related to what they'll be asking. So we'll reverse order here. Kate, if you're there and would like to ask another question of Kristen, that'd be great.
Yeah, Kristen, I don't know if you're aware, but well, you probably are. The eligibility for the vaccine in Washington State is, and in terms of education, is only for K-12 educators. And so they have not added higher education instructors, even with the new guidelines for next week. So I'm curious if you know why, considering, college students are less likely to practice social distancing and wearing masks, as we saw recently from the pictures in Miami with spring breakers. So I'm wondering if you have any thoughts on that.
I am not sure how much the behavior of the students was taken into account when the vaccine prioritization was done. But personally, I think anyone who has to work outside their home and interact with the general population or a population like students should be eligible for the vaccine, because they're just at greater risk of encountering someone who is sick. It's interesting, there's been a lot of discussion among public health people about whether or not we did the right outreach to the community of college students and millennials who early on didn't seem to be a big factor in spreading the virus, but have certainly caught up to it. And hopefully we'll be able to continue to communicate with them and make that communication more effective.
Thank you. Thank you, Kate. We'll go to Loanne.
With schools back in session, more kids are bringing home runny noses. And so more employees are getting the symptoms of colds, but they might be COVID. So as an employer, we request a COVID test. And then we're hearing about false negatives, and that's really disconcerting. So what advice do you have to employers regarding symptoms versus test results?
Sure. So there are false results with this test. But they are primarily in the antigen tests. So if you're requesting PCR tests are pretty reliable. The main thing that can go wrong in a PCR test is incorrect collection of the sample. And all of our folks who are collecting samples right now have a tremendous amount of training. They're really good at that. For the antigen test, I'd advise anyone with symptoms who's going to get an antigen test to get tested promptly. We know the antigen test works best right after you develop symptoms. The longer that you wait to go get tested, the more likely it is that your immune system's fighting off the virus and you're going to get a false negative result. So if someone thinks that they have COVID-19, I'd either request a molecular or PCR test or request a very prompt antigen test. And if it's negative, then I would look at what else is going on. Does their child have something and it's also not COVID? Are the spring trees blooming? Right. I know that this week my nose is running and I'm pretty sure it's the spring trees. So I would look at what else. But I think you raise an excellent question, which is, I think for a while, every time someone gets sick, employers are going to wonder what it is and if it's COVID.
Thank you.
Thank you, Loanne. We'll go back to Martine.
Thank you. So one of the things that I know that now different groups are now eligible, and one of the groups that was recently eligible is pregnant women. But I was speaking with somebody recently, and they were concerned about that, and I hadn't read any concerns about the vaccine and the reaction to either the pregnant woman itself or a fetus, the baby. So I don't know if we have any data on that or any research.
Interestingly, there's more than you might think. Because of ethical concerns, in the US, we don't test pregnant women in clinical trials, but that didn't stop women from getting pregnant during the clinical trials. So in all of the clinical trials, there were somewhere on the order of 1,000 women who got pregnant and didn't see any adverse reactions with the vaccine. So that's really good news about pregnant women. And I think that's one of the reasons that they are starting to look at whether or not pregnant women should be prioritized for getting the vaccine.
Great, thank you.
Thank you, Martine. We'll round out with the second question from Justin, please.
The AstraZeneca vaccine has been in the news a lot recently. I wonder if you can comment on its current state regarding recent temporary suspensions by several European countries of using it, and last night's statement from the National Institute of Allergy and Infectious Diseases about data concerns that might delay that vaccine's approval for use here in the US.
Yeah, you know, the AstraZeneca Oxford vaccine is based on the same technology as the Johnson & Johnson. So scientifically, I don't have any doubts that that should be a good vaccine. But as Dr. Fauci described it this morning, its rollout has had some unforced errors. So early on, they had a problem with their dosing. So one of their cohorts received 2 different doses of the vaccine, which was unplanned. And of course, now we're seeing the release of data, but it's not the most current data, and some concerns about blood clots in European countries. The reports of blood clots are concerning, but I'm not yet convinced that there's a demonstrated link. And I was just reading today, the UK went back and looked at their data, and they are not seeing any correlation with blood clots in their data. And I believe they are going to move forward with giving the AstraZeneca vaccine again. But I do think it's good. The company has been warned that they're going to get a lot of scrutiny when they go before the FDA, and that their data is going to get a good scrubbing. And I think that's good because they haven't been fully coordinated or fully transparent in their rollout of the data. And if we have a good scrubbing by FDA, I hope that if there are any issues, that process will uncover them.
Thank you.
You know, personally, I'm a mother, and AstraZeneca was the first to start clinical trials on kids down to the age of 6. So I was really sad to see them kind of stumble in this because they are the most likely to get to elementary age children.
Okay, thanks, Kristen. Let's get through some more questions here in the chat. Again, thank you to all the audience members who are typing these in. We've got some really great questions coming through. So Kristen, you did a nice job explaining the different ways that the vaccines work. Let's talk about developing antibodies only against the spike protein. Immunologically, what effects might that have versus getting vaccinated with an intact virus and more regions?
Ooh, interesting. So the S protein is what allows the virus to get into your cells. So by specifically targeting S, what we're targeting is getting your body to produce the machinery that blocks it from getting into cells and labels it for destruction. So there is a general sense that by targeting S, we will end up with more effective vaccines than by other methods. But that's an interesting concept of an attack virus that I don't think I have seen in any of the lists. All of the technologies that we're using to develop these vaccines had to be in some state of development, some state of clinical development prior to the coronavirus pandemic. So I don't think we are seeing truly novel platforms coming online with this, simply because of the timescale. That platform already had to be in development. The Moderna platform and the Pfizer platform, they were already in development before we got here. So what we're getting is what we could roll out in that period of time. But I do think targeting the S gene is a really effective strategy, because that is blocking that S glycoprotein is going to be a good way of blocking that virus from infecting your cells in the first place.
Great, thanks. Out of curiosity, when you were talking about the variants, I think you mentioned about 10 amino acids might be changed in the S protein. How does that stack up relative to other viral mutation percentages? Is that a lot? Is that hardly any?
Hardly any, actually. So this virus is mutating more slowly than influenza or HIV. And Amy Sims understands this better than I do, but there is a proofreading function in coronavirus that keeps it from mutating too much. So it is not a rapidly mutating virus. And And that is one of the reasons that I think the scientific community is watching this so closely, is we know it's not a rapidly mutating virus, but we are getting to the point where we're seeing it mutate into, a new mutation is taking over in California. It's like 30% of the cases in California now. So that behavior indicates that the virus has been out there long enough that it is starting to accrue some of these mutations, and that there might be more to come.
Gotcha. Thank you. And could I just clarify that when we say S protein, spike protein, that's a synonymous term?
Yes, that is to say S antigen, spike protein, spike glycoprotein are all different ways of referring to that little crown feature that sits on the virus surface.
Great, thank you. Okay, the CDC suggests that if someone has been positive for COVID, they should wait something like 90 days prior to receiving a vaccine. Why is that?
I don't know, actually. I could look that up and see what the rationale is behind that, but I hadn't heard that yet.
Okay, I was just wondering if it maybe was related to a natural immunity that's starting to wane after that point of time, or a potential for a more severe reaction if you're very recently infected.
One of the things that they're seeing is that people who have had COVID do have a more severe reaction to their first vaccine. My mother-in-law had COVID, as did my sister-in-law, and they were both knocked for a loop by their first vaccine. Most people get knocked for a loop by their second vaccine. So there seems to be something about that second exposure that really builds up the immune system, but can also cause some serious side effects.
Perfect, makes sense. Okay, let's see. Since both Pfizer and Moderna vaccines protect against they're designed against the S protein, they're mRNA vaccines, they both have EUA, why is it still not recommended that you could get one dose of each?
Because that hasn't been studied. And actually the UK is starting to study that. So the way that we approve vaccines in the US, the manufacturer has to make them a certain way, store them a certain way, and administer them a certain way. And then what we approve goes through the whole thing. So that's one of the reasons why the Pfizer and the Moderna have different storage requirements, is because that's what the manufacturer tested. So until we have test data, we won't approve that, or we won't emergency use authorize that. CDC is saying it's probably okay. And I would say as a scientist, it's probably okay under extraordinary circumstances, but they are still recommending that in general, if you can go with the regimen that was what was tested, that you do that.
That makes sense, okay. So kind of in line with that, if different vaccines target different parts of the virus or designed in slightly different ways, is there any benefit, maybe in the long term once supply is not short, would there be benefit to getting multiple types of vaccines against COVID-19?
That's a really interesting question. And that's something that we haven't really studied yet, but I think that is something that will be studied ultimately. One of the other things they're talking about is maybe a third booster to protect against some of the variants.
Cool, okay. Let's see, jump back to testing real quick. Is there any possible ways to test how severe a person is going to be affected by the virus, or any tests you could do in conjunction with a COVID-19 test to say whether or not you're likely to get really sick?
Not easily. And that's because this virus, we haven't really been able to figure out what we would test for that would indicate the severity with this virus. There was a really interesting study done by FDA where they looked at test results, and you would think that the concentration of the virus in somebody's specimen would somehow correlate with disease severity. That's, as a scientist, that seems like it makes sense to me. We're not seeing that with this virus. There are people who are actually walking around asymptomatic with fairly large concentrations of the virus in their system. And we don't understand why that is. So I would love it if we had a test that did that, but I think we're a ways away from that.
Gotcha. Okay, we're just about out of time here. I wanted to ask one last question. Maybe we could hopefully leave on a little bit of a reassuring note. So there's been a lot of information or worry about maybe these new mRNA vaccines having the ability to incorporate or affect our own genetic material. What can you say about that and whether or not that's a possibility?
Yeah, that's an excellent question. So when people hear nucleic acid vaccine, that is something that they worry about. Those lipid nanoparticles that encapsulate the mRNA in the mRNA vaccines are capable of getting into your cells, but they're not capable of getting into the nucleus, which is where your genetic material is. So they get into the cells and they drop the mRNA, which can make the spike glycoprotein out in the cytoplasm of the cell, but they never end up in the right place at the right time so that they could incorporate into your own DNA.
Cool, that makes sense. Thank you. Well, we're at 6:15. Really want to thank you again, Kristen, for the time, especially the extra time to answer the questions. We unfortunately hardly put a dent in. Thank you to all the audience who were attended and so engaging in the chat. Thank you to our community panel, Loanne, Kate, Martine, and Justin. It's always great to see you and hear from you. Would just like to plug one last reminder. So next week, Tuesday the 30th, we'll be having our last talk of this series. We'll be hearing from Tim Scheibe. His talk is titled Model Me This, COVID-19 Scientific Predictions and Where We Go From Here. It's 5 p.m. here on Zoom. The registration link is in the chat window. It's also the same website where you can go find recordings of the previous talks if you weren't able to attend those, as well as information about other community science and technology seminars presented by PNNL in the future. So with that, I'd just like to wish everyone a nice evening and say I hope to see you next week. Thank you.
Thanks, Jim.